No, just thank you all for giving me this chance to talk to you and present some of our recent work. So I'll be telling you about some of the work in Dan Stamperkern's group at UC Berkeley, realizing multimode cavity optodynamics with collective atomic motion and spin. And kind of, I guess, suggest that my overall outline for this talk is going to be a really bottom-up kind of approach to this many-body cavity QED. First, introducing just the optodynamics of kind of single collective modes of the atomic motion or the atomic spin, and explaining how we can control and measure those using an optical field. And then once we have those tools, I'll explain how we can start building them together using the optical cavity to mediate interactions. First, demonstrating coupling between the mechanical oscillations of two ensembles of atoms. And then next, I'll show a recent demonstration of so-called negative mass instability, realized when coupling the collective motion and spin of a single ensemble of atoms inside the cavity. And then in the remaining time, I'll try to cast this bold vision, as Dan suggested, for some future directions that we might be able to take with this work. So to begin with, I'd like to kind of suggest a general description for the field of cavity optodynamics, which is really using an optical cavity in particular to probe the dynamics of often a macroscopic system. And this can give a very sensitive probe of the dynamics of the system, realizing kind of basic models of quantum measurement, but then also with sufficient coupling strength, be able to realize optical backaction onto the dynamics of the system, modifying the behavior, and in particular to the point where the quantum mechanical nature of the probe field can lead to quantum backaction due to the measurement of the system. I mean, this is probably most familiar in the world of optomechanics, using the light to measure the motion of a mechanical oscillator, so harmonic oscillator being kind of our favorite degree of freedom as physicists. And this is maybe most familiar in terms of a Fabry-Perot cavity with a harmonically confined mirror. But I think, as all of us are probably familiar, there's been kind of a large history of development in this field demonstrating such effects in all sorts of different kinds of systems, and really pushing the boundary in a lot of these nanomechanical devices of high-quality oscillators and very strong measurement coupling in the system. And this has enabled a lot of previous demonstrations of actually demonstrating quantum mechanical features of these macroscopic systems, such as cooling the mechanical oscillators to their ground state, generating mechanically squeezed state of oscillators, and then also demonstrating backaction evasion to overcome standard quantum limits that arise from the quantum nature of the field. I think it's useful to think about this kind of general picture of cavity optodynamics because there are other systems, in particular spins, that we can consider probing with an optical cavity. And I think in the macroscopic world, this has seen a lot of recent development in a field which has been named optomagnonics, where people have started demonstrating the coupling of light, or particularly the polarization of light, to macroscopic spin degrees of freedom, or magnetic domains within solid-state systems such as yttrium ion and garnet spheres. And this has led to some recent demonstrations of quantum mechanical features as well, realizing effective spin orbit coupling for photons in the system, or demonstrating microwave to optical photon conversion and backaction cancellation. So these are kind of very macroscopic systems that these effects have been demonstrated in, but of course, atoms provide a very compelling system to realize both of these types of dynamics, which I think kind of really unites these two pictures together into this field of cavity optodynamics. And a lot of work has been done demonstrating related optomechanical coupling or coupling to the spin of the atoms. But an essential ingredient in all of these kind of quantum mechanical effects that we might be able to probe is that we need to be able to prepare the dynamics of the system in a pure quantum state. And so that implies cooling the oscillator to the ground state. And that's, while that's an obstacle or a very big challenge in a lot of these macroscopic systems, we can realize this very well in our lab using kind of a tunable atomic cavity optodynamic system. So, of course, using standard atomic physics techniques, we can prepare an ultra-cold ensemble of atoms and spin polarize it so that we can start near the ground state of both the motion and the spin of the atoms. And I think, like we heard about yesterday, we use an atom chip in our lab to transfer the atoms into the mode of an optical cavity. And similarly, this gives us sub-wavelength precision of placing the atoms inside the optical cavity. We can use that to load the atoms into a single node of our optical dipole trap, which is resonant between the cavity mirrors. Once we have the atoms trapped inside the cavity, then we can probe them by dispersively coupling the atoms to a second probe mode of the cavity field, which is far tuned away from the atomic D2 transition. So using this basic system, we can realize an optomechanical coupling, recognizing that the center of mass axial motion of the atoms inside the dipole trap for small excitations is approximately harmonic. And so this represents the harmonic oscillator in our system. And then by using our control of the placement of the atoms, we can choose to place the atoms at the linear slope of the probe mode intensity within the cavity, realizing the maximum intensity gradient, which gives us a position-dependent dispersive interaction of the atoms with the light. And this interaction kind of realizes the basic optomechanical model. And there's two different ways that we can look at it. One, recognizing it as an energy proportional to the photon number, it represents a position-dependent frequency shift of the cavity field. And this facilitates a continuous measurement just by monitoring the frequency or modulation of light transmitted through the cavity. In addition, recognizing it as an energy proportional to the position, it represents a radiation pressure force that's proportional to the intensity of light inside the cavity. And this is where the quantum mechanical nature of the shot noise fluctuations of the photon number within the cavity implies measurement backaction onto the dynamics of the oscillator, corresponding to our measurement of its position and satisfying, therefore, the Heisenberg uncertainty principle. So this kind of introduces the basic essential pieces for an optodynamical system. So I'd like to kind of refocus now and talk a little bit more about the spin dynamics, which maybe is not quite as familiar in this context. So we can realize a very similar type of interaction by looking at the Larmor precession of the spin in a transverse magnetic field, such that the spin precesses in the plane of the cavity axis. Placing the atoms at the maximum intensity of the probe field now, we can suppress any sensitivity to the motion of the atoms and achieve a spin-dependent coupling by driving the cavity with circularly polarized light. This arises because of the circular birefringence of the polarized ensemble of atoms, which gives rise to a spin-dependent dispersive shift that is sensitive to the projection of the total atomic spin along the cavity axis, giving us sensitivity to this kind of oscillating component of the precessing spin. And again, in addition, this interaction also looks like an effective optical magnetic field that acts back onto the motion of the spin. And this arises from the vector AC Stark shift that the atoms experience from their interaction with circularly polarized light. So in both of these cases, the cavity field introduces this open quantum channel into the system. Sorry, I'm getting ahead of myself. I guess before I move on, I'd like to point out a couple distinctions between the spin and the mechanics. And one of them that immediately jumps out is that the spin oscillator has, in addition to a ground state, also a highest energy state. And that means that there are two stable points of the dynamics where the amplitude of the precession goes to 0. And this will kind of give us some unique tools that we can use later on, combined with the mechanical oscillator. In addition, I'd also point out that the spin oscillator is not subject to damping by a thermal bath. And so there's kind of negligible decay that we see for the spin oscillator in our system, which is also a unique feature. So as I was starting to get carried away saying, the cavity mode, of course, introduces this open channel that we can use to interact with the system. And so we can probe the cavity and then measure the light coming out of it. And in particular, if we probe the cavity on resonance with the drive, then the atomic dynamics will just modulate the phase of the light, and that light exiting the cavity we can detect with an optical heterodyne detector to get a real-time measurement of both the motion and spin of the atoms. But more interestingly, if we probe the cavity off resonance, then as the atomic dynamics modulate the cavity frequency back and forth, this is going to cause amplitude modulation of light inside the cavity. And this creates an effective feedback loop where now the motion of the oscillators modulated onto the amplitude of the cavity light act back through these effective magnetic fields or radiation pressure force onto the subsequent dynamics of the oscillator, and modifies the response of the oscillator. And also later on, this is the effect that I'll use to demonstrate coupling between two oscillators. We can this feedback process is mediated by the cavity field and kind of conditioned by the cavity line width. And so, for instance, we can demonstrate this with a high energy spin oscillator that by creating or coherently rotating the spin away from the high energy state, then applying and driving the cavity above cavity resonance, we realize negative feedback, which tends to damp the Larmor precession of the spin back toward the high energy state, as shown here in the real-time signal that we see exiting the cavity. Conversely, we can also realize positive feedback from this interaction just by detuning the probe to the other side of cavity resonance. And now, starting with a high energy spin, we amplify the spin away from the high energy pole, causing the amplitude of precession to increase until eventually it actually wraps around the equator of the black sphere and damps back to the low energy pole of the system. Now, both of these demonstrations are really just showing kind of coherent and essentially very classical dynamics of being able to amplify and damp the coherent motion of the spin. But this process is also going to be limited by incoherent backaction from the quantum mechanical nature of the field, and that will cause this stabilized spin damping it either to the high or low energy pole to realize an effective temperature in equilibrium with the measurement backaction, which drives diffusion of the spin away from the ground state. So we can measure this in our system by applying a damping tone on either side of cavity resonance, and then use a second weak tone on resonance with the cavity to measure the Stokes and anti-Stokes sideband asymmetry of light scattered out of that carrier tone from interaction with the spin. And looking at the asymmetry of the light in the Stokes and anti-Stokes sideband reveals the absolute temperature of the oscillator, because a near ground state harmonic oscillator or spin oscillator can no longer give up energy to the light, and so the anti-Stokes sideband will be suppressed, revealing the temperature of the system. Now, taking advantage of this highest energy state for the spin, we can look at a spin that is stabilized near that high energy state and demonstrate that the sideband asymmetry is reversed, reflective of an effective negative temperature of this inverted population of the spin ensemble. And furthermore, we could demonstrate that as a function of the Larmor frequency of the spin, as we increase the frequency, this equilibrium temperature approaches zero, bringing us toward the pure quantum state in the system as we increase the Larmor frequency relative to the cavity line width. And this just is reflective of the fact that the cavity can better suppress the Stokes or anti-Stokes scattering of light from this damping tone, giving us a more and more coherent damping process. So I'll kind of take this one step further then and say this negative temperature oscillator, if we consider now the collective excitation of the spin away from this high energy pole, we can also describe it as a negative mass or effective negative mass oscillator. And this can simply be understood that as we increase the amplitude of the precession, we're lowering the energy of the system, which just looks like an inverted ladder of harmonic oscillator states. And in this analogy, I think it's helpful to think about the transverse spin precession as the motion of the oscillator in phase space, basically rotating through the position and momentum of this effective oscillator. So this kind of concludes my introduction of the basic building blocks that we have in the system, and I think demonstrates the essential parts that I suggested of realizing ground state oscillators and then backaction limited measurements of the dynamics in our system. So now I'd like to talk about how we can put these together and realize these cavity-mediated interactions, first of two mechanical oscillators inside the cavity, with the goal of being able to build toward truly many-body types of physics. So just to begin with a very quick picture of, or a reminder of what coupled oscillators are like, we can think of the dynamics of these two oscillators in phase space, again, as just the rotation of this complex amplitude of the oscillator's mode. And then adding a effective spring-like interaction, we're all familiar that in the rotating wave approximation, it's the counter-rotating terms of this interaction that survive. And this gives us this effective exchange interaction, which conserves the total number of excitations and just allows us to transfer the state of the oscillators back and forth. If we consider the eigenvalues of this interaction, we know that this, of course, gives us the familiar avoided crossing in the energy spectrum for the two oscillators. So we realize this in our system by actually loading two ensembles of atoms into now a superlattice potential formed by the interference of two optical dipole traps inside of our cavity, one at 840 and one at 860 nanometers. Because the cavity now measures the sum of the displacement of the two oscillators, the superlattice potential resolves the frequency of neighboring wells, so that now looking at the spectrum of light exiting the cavity, we can clearly distinguish the motion of the two ensembles. So now, using this feedback mechanism that I explained before, we can also mediate coupling between the two oscillators, which we can control by increasing the detuning of the probe from the cavity field. And what we see as we do so is that the response of the two oscillators in the spectrum does in fact start to repel and move apart from each other in frequency. But at the same time, you might notice that one of these modes gets larger and the other one gets suppressed. And this is because the normal modes of the system hybridize into a center of mass mode, which is bright with respect to the cavity, and a breathing mode of the system, which becomes dark because the cavity measures the sum of the motion of the two oscillators. But this demonstrates the hybridization of the normal modes, but we wanted to take this a step further and actually demonstrate coherent transfer of the state between the two oscillators. To do this, we shake the optical dipole trap at the frequency of one oscillator, creating a coherent excitation, and then couple the oscillators for variable amounts of time, allowing that excitation to transfer to the other oscillator and then back. Stopping this process after some amount of coupling time, we can then measure the free transient decay of the state of the two oscillators that we've created. And I think most notably, we notice that when the oscillators share parts of this coherent excitation, we see this clear beat note in the signal that we measure exiting the cavity, which is just reflective of the sum of the two oscillators, or the coherent sum of the two oscillators' displacement as it rings down. We can effectively filter this signal using our knowledge of the frequency and line width of the mechanical oscillators and just fit it to a sum of two decaying sinusoids to extract the amplitude and phase of the coherent displacement of the oscillators, which gives us this red signal that we see here. Similarly, we can also extract single-shot estimates of the amplitude and phase from each iteration of the experiment. These data are showing averages over many, many iterations, I think a couple thousand in this case. But doing this on a single-shot basis allows us to actually look at the distribution of final states of the oscillators. And this is where things start to get interesting. So this is, if we just look at the initial state of the oscillator, we see that the variance of this distribution is given by the sum of two parts. This inner circle, which might be a little bit hard to see, is the shot noise variation due to our measurement. So that's just the measurement noise that is added to the system. And so the difference between that and the total variance of the distribution is the number of thermal phonons in the system. If we look at this distribution immediately after the excitation pulse, we see that there's a coherent displacement of the first oscillator, but the incoherent distribution looks mostly the same. But then after some amount of coupling time, we see that while this coherent excitation is now shared between the two oscillators, which reflects the same exchange that was showed on the last slide, we now find that the incoherent excitation, the number of added thermal phonons in this distribution, has grown. And we can look at this as a function of the coupling time, and we find that the number of added thermal excitations in the system exhibits nearly linear growth, which is well explained just by the effect of measurement backaction on the dynamics of the system. And you might notice here that one of the oscillators actually gains more backaction noise, and that's because we haven't fully hybridized the system into the center of mass and breathing mode. And so the bright mode of the system has a larger component of oscillator 2, and so it exhibits a larger degree of backaction noise. An interesting feature that emerged in this work is that the two oscillators are coupled to the same cavity mode, and so they actually exhibit quantum fluctuations, or the same quantum fluctuations, in this backaction noise. And this leads to a correlation between the distribution of the two oscillators, which also grows weakly as a function of the coupling time, and demonstrates essentially the quantum mechanical nature of the spring that we're using to couple the two oscillators, because the lossy cavity that's mediating this interaction leaks information to the outside world. So I'll move on, but come back, I think, at the end toward some interesting applications we might be able to realize with that. But the next part I'd like to focus on a recent demonstration of this effective negative mass instability of coupling the negative mass spin oscillator to the positive mass motion of the ensemble of atoms inside the cavity. And to start with this, I think it's easy to understand if returning to this basic picture of a harmonic oscillator, where the negative mass harmonic oscillator just flips the sign of its contribution to the Hamiltonian, which causes it to effectively counter-rotate in this phase-space picture. Under the rotating wave approximation now, it is instead the pair creation and pair annihilation terms that survive. And this leads to an interaction that does not conserve the excitation any longer, but instead we can create pairs of excitation in the two oscillators without any energy cost, leading to amplification of a correlated mode of the system, much like an optical parametric amplifier, in fact. Again, if we look at the eigenvalues of the system, here we find that the frequency, which is given by the real part of the eigenvalues, now actually synchronizes together in the region of strong coupling, in which case the eigenvalue becomes complex. And the imaginary component refers to the intrinsic amplification and damping of this normal mode of the system. So we can try to probe this again in our experiment, this time just using a single ensemble of atoms and looking at the coupling of its motion and spin. We prepare both of them near their ground state and then ramp their frequencies together to a desired tuning before turning on the coupling for some chosen amount of time. After that, we pull the oscillators back apart and again look at their free decay to learn about or measure the final state of the system that we've created. Similar to before, the cavity is going to measure some sum of the displacement of both oscillators, but in this case, because we start near the ground state without a coherent excitation, this average cavity signal I started with before is no longer going to tell us anything about the dynamics, because this instability is going to amplify the system with a random absolute phase. So instead, we can see this growth and correlation of the dynamics in the mean square displacement signal, which we can write in terms of the states of the two oscillators in this way. And there's really two different groups of terms that are interesting in this picture. These first two just reflect the occupation of the two oscillator and show the exponential growth of the occupation during the instability process. And in addition, these last two terms represent a heterodyne-like or self-heterodyne-like beat note that measures the two-mode coherence between the two oscillators. And this becomes clear when we uncouple the oscillators and look at their free ring down after resolving their frequencies, and we can see the evolution of this beat note at the difference frequency between the two oscillators. And this directly reveals the magnitude and phase of correlations that we've created in the system. Similar to before, we can extract single-shot estimates of the amplitude and phase of each oscillator, and looking at the distribution of these, we can then uniquely identify the occupation and correlation in the system. And so looking at this as a function of the coupling time, and the red and the blue triangles here to show the exponential growth of the occupation of both oscillators for short coupling times, and eventually the system saturates at longer coupling. And what's interesting is that we can also then look at this correlation magnitude between the two oscillators and see that the growth in the system is well accounted for by correlated excitations that are added between the two of them. Stopping this process kind of before the saturation, we can then also look at the dependence of this instability on the detuning between the two oscillators, where as we vary that detuning and measure the magnitude and phase of the correlations that we've created, we see that as expected from the eigenvectors of this interaction, the relative phase between the two oscillators at the peak of the instability is exactly pi over 2. Although, as you might notice, there's a small shift of the data away from our expected theory, which we don't entirely understand, but I guess I should start by saying the expected resonance of this is shifted away from the zero detuning case between the two oscillators because of optodynamical spring shifts, but the size of the shift that we measure is a little bit larger for reasons that we can't quite explain. So I guess at this point I'd like to kind of start transitioning toward some ideas of what we might be able to do with this. You might be thinking, because as I mentioned before, that this interaction, this pair creation dynamics is a lot like the dynamics of a parametric amplifier. And so, as in the case of non-degenerate parametric amplifiers, you might expect that this could create two-mode squeezing between the motion and spin of the oscillator. Unfortunately, this is not possible for us to observe with this system because in coupling the spin and motion of a single ensemble of atoms, we also realize an incoherent coupling between the spin and motion of each individual atom because of the spatial variation of the AC start shift that we realize in the interaction with the optical lattice, with the optical probe. And this leads to just incoherent dynamics that obscures any potential squeezing we might be able to realize in the system. But more fundamentally, you might also realize that, as I demonstrated before, this interaction, because of the quantum nature of the coupling field, introduces a lot of backaction into the system. And that leaves open this question of, in this unresolved sideband regime where the cavity provides a very good measurement of the dynamics of the system, but also introduces a lot of backaction, can you actually realize a quantum mechanical state of the system? And this leads to an interesting realization that has been pointed out, that actually as we detune the probe from cavity resonance, while it reduces, for much larger detunings of the probe, the coherent interactions become weaker, we actually suppress the backaction, or the incoherent part of the interaction, much, much faster. And so for even in this unresolved sideband regime, the detuning of the probe, or for detunings of the probe much larger than the cavity line width, we can actually make the process more and more coherent. And so this seems to be implied as well by our theory calculations for this spin mechanical coupling, where at a large detuning from the cavity line width, it would seem to imply that we could take even an initially thermal state of the oscillators and be able to see a transient squeezing effect during this coupling process. And this really arises because of the damped normal mode of this interaction, which I've kind of neglected speaking about so far, but I guess could be used to prepare a two-mode squeeze state. In addition, one other potential application of this is using it as a quantum-limited amplifier for the optomechanical state, which could be used to overcome limited detection efficiency to realize kind of beyond SQL measurements of an optomechanical system. So in my remaining time, I'd like to consider some other future directions that we might be able to scale these kinds of interactions up to. And so one natural direction that I think this leads into is to consider going from 2 oscillators to n oscillators, and actually looking at many body dynamics. And I'm not going to say too much about this. I think the extension, it's kind of intuitive how this might go, but just by adding more and more ensembles of atoms into the cavity, then if you can control their frequency or selectively address them, then you could use the cavity to couple them in pairs or create different kinds of interactions between the two. And using these two different types of interactions that we've demonstrated, you could create exchange of excitations or actually generate squeezing and entanglement of selected modes within this many-body system. And the cavity provides a nice kind of multiplexed readout where you can see and resolve the motion then of many modes of freedom within the cavity. But so instead of kind of considering further what we might do with that, though, I'd like to shift into a different direction and actually suggest an idea or describe an idea that we're starting to pursue of actually stabilizing an oscillator outside of equilibrium. And we can realize this with the spin inside of our cavity by actually applying the magnetic field at a small angle away from the cavity axis. And what this does is it introduces a sensitivity to the dynamics of all three components of the spin inside the cavity, where the transverse precession of the spin modulates the cavity at the Larmor frequency, again leading to these kinds of optodynamical feedback effects. But in addition, now the longitudinal component of the spin has some average projection along the cavity axis, and this is going to lead to an average shift of the cavity resonance frequency, which I've just kind of mapped out here in frequency space, that for a high energy spin, it'll have a positive shift, and for a low energy spin, it will have a negative shift. And so this leads to a sensitivity of the cavity to the total energy of the spin processing in this magnetic field. And then we can use this optodynamical interaction to feed back to that. So for instance, if the probe is attuned above cavity resonance, it's going to tend to add energy to the spin oscillator, or below resonance, it'll remove energy from. And this can realize a negative feedback situation where the optodynamical process will tune the spin of the energy, or the energy of the spin, to actually bring the cavity resonance, or to resonance with the probe. And then we can control and tune the polar angle of the spin, or its equilibrium energy, by just tuning the cavity drive within this spectrum. And what we realize when we do this is that we have a spin oscillator stabilized at a specific polar angle that is chosen by the frequency of the probe that we apply to this cavity, and any fluctuations of the spin away from that polar angle will be damped back to equilibrium. And so this would provide us with an oscillator in an out of equilibrium steady state, and we're really just starting to explore kind of some of the basic demonstrations of this interaction, and so we're still open to kind of generating ideas about what this might look like, or what kinds of fluctuations we might expect to see for this non-thermal state of the spin. In addition, I think there might be there's an interesting direction that we could go, that there are very strong nonlinear dynamics that can be easily introduced into the system just by tilting the magnetic field away from the cavity axis further, introducing larger amplitude modulations of the field. And these have been partially explored in some of the early optomagnetic work as well. So with that, I'd like to recognize everyone that I've worked with on all of these projects, in particular Justin and Emma, who are here and worked on this negative mass instability, but are also building a new cavity experiment in the lab, so you should talk to them about that. And with that, I thank you for your attention.
Last thing you talked about, which is stabilizing the spin out of equilibrium. I don't quite understand how that works, but I'll ask you later. But it reminds me of many schemes for sort of back engineering or autonomous state stabilization that explore super effective circuits. And in those cases, you can think of it as you apply all these drives and you create some new system, and your stabilized state is now the effective ground state of that new Hamiltonian. You want to think about this in the same way?
I'm not sure yet. I've started thinking about that, and I've been suspicious of that in the same way myself. Yeah, I think what it might arise is that when you eliminate the cavity field from the system, that it might be that there is some effective potential that can describe this. But yeah, we haven't really explored that direction too much yet.
One of the aspects that's weird is that if you displace the system from equilibrium, it doesn't oscillate about that point at all. It simply damps right back.
So it's critically damped to that point.
Yeah,
the
so
potential
that's
is about
describing it by Hamiltonian. What's really the utility?
Yeah, well, it's just maybe a nice way to think about it, that it's you create this new thing, now that's your ground state. That makes sense. Maybe it's saying deeper than that.
Any other questions?
I was wondering whether, so I love just this idea of coupling spin and motion, and I'm wondering whether there are things that you can more easily with one or the other in terms of either state preparation or detection, that you can then sort of use the cavity to transfer one way or the other?
Yeah, so as I mentioned maybe briefly before, they do have fairly different properties. So the mechanics is damped to this thermal bath, and so it tends to kind of always acquire some thermal temperature, whereas the spin, at least we can begin with in a kind of very pure state from optical pumping. And actually, the lack of damping there for the spin is kind of both a benefit and also sometimes a difficulty, because any measurement backaction that's added to it never really damps away, and so it tends to just kind of diffuse without bound. And so, yeah, I think in that way it's well, and actually, I guess one comment related to that I could would back up to say is that the squeezing that the theory tends to predict that we could see is actually critically dependent in some ways on the damping in the mechanical oscillator, and that it requires some of that dissipation, I think, to actually be able to realize this state. Yeah, I mean, maybe that doesn't maybe fully answer your question, but some of the ideas. Yes?
Sort of as a follow-up, firstly, what limits the Q if you're not measuring the mechanical oscillator? Is it inhomogeneous corrupting?
We suspect it's due to a couple of effects, potentially due to collisions between all of the individual atoms inside this ensemble. And so we tend to think of the motion of all the atoms relative to the center of mass as some kind of effective thermal environment that the mechanical motion is coupled to, whether it's by inhomogeneity of the trap or actual collisions between the atoms inside the ensemble.
Okay, and then the follow-up is, so you made this comment that you need the damping for some of the physics that you want to explore, but I can also imagine that having a higher mechanical Q in some sense makes your oscillator more coherent. So that also has to be a good thing. So would there be a regime of experiments that would open up if you had a factor of 100 higher Q for the mechanical oscillator?
I think that's certainly true, and many of the other platforms that I illustrated at first for these optomechanical systems have Qs that are factors of thousands or tens of thousands or many, many times higher, and that is part of what enables them to realize these more quantum mechanical nature. In our case with the atoms, we benefit because we can start near the ground state, and so we don't need the Q of the oscillator to actually allow us to cool it to the ground state as well. But I think it's true. Having a more coherent oscillator in some ways can only help with realizing these kinds of coherent manipulations of the system. Anyone else?
No more questions. Let's thank Jonathan and Dennis.